This is an introduction video about DVTOP. DVTOP is a dynamical visualization tool for optimization problems. In our daily life, there are many fields that need to address optimization problems, such as deployment problem in wireless sensor network, the stock selection problem, and the circuit synthesis problem. All of these problems just want to reach the goal that minimize cost and maximize profit as they can. These problems can be roughly divided into two categories: the numerical optimization with the continuous variables and the combinatorial optimization with the discrete variables. We take the stock selection problem as an example. When we have three stocks, Apple, Microsoft, and Google, if we want to choose all of them into our portfolio, the combination will be 111. We can know that all of the combinations are 2 to the power of 3, 8 combinations. We want to add the Amazon into our target. Now we have 4 stocks or items. The possible combinations are 2 to the power of 4, 16 combinations. But if we have the 50 stocks in our target, the complexity is 2 to the power of 50. The possible combinations are over 1,000 trillion. It is a tremendously huge number. As this optimization problem is so complex and difficult, the best solution cannot be searched within a short time. Therefore, the researchers applied the meta-heuristic algorithm to solve such a huge solution space problem and try to find a near-optimal solution. There are many kinds of meta-heuristic algorithms, such as genetic algorithms, the particle swarm optimization, and the artificial big learning algorithm. To test the effect of the algorithm, one of the numerical optimization problems is functional optimization. The researchers experiment on these complicated functions, such as Schwaffel, Mikhailovich, and Eckley, to find a minima or maxima value. However, it is so hard to imagine what does the function looks like just by looking at the equation. The researchers used to observe and analyze the algorithm's solving process by text log file, command line, DOS, and Excel to display or output the results. Taking the particle swarm optimization, PSO in brief as an example. PSO imitates the movement of a bird flock. The yellow line demonstrates the first generation position. The green line demonstrates the second generation, and the pink line demonstrates the third generation. We just want to know the movement direction of each particle. We have to check all of the positions one by one. But the algorithm includes just 10,000 generations and 20 particles. There are 200,000 positions that need to be checked. Not to mention that the more generations or more particles. If we want to carefully recognize the moving direction, that could be very unintuitive, time-consuming, and difficult to analyze. When there is a mistake in the analyzing process, all the efforts are wasted. So it could be impossible to analyze all the positions by the traditional method. Therefore, this study developed a visualization tool, DVTOP, to dynamically demonstrate the algorithm solving process in these complex optimization problems. DVTOP can enhance the efficiency and lower the burden to the analysis, and making the solving process clear and vividly interesting. The following is our functional demonstration. DVTOP has two categories of interface. The first introduced is the numerical optimization tool. In this interface, the upper white box is the function we input with the latex form equation. The right color bar represents the fitness that corresponds to the solution space. The red to blue color represents the height to low fitness. DVTOP can display many kinds of benchmark functions, such as Restron, Rosenbrock, Schwaffel, and Himmel-Blau. DVTOP can also show the detailed information in each generation to assist observing the execution process more conveniently. In DVTOP, we use the different images to represent the different particles and different tracks. Researchers can change the image according to the algorithm, such as the well optimization algorithm, the Jaga algorithm, the artificial bee cloning algorithm. In ABC, we use three kinds of bee images to represent the employee bee, onlooker bee, and scout bee. Traditionally, researchers can only use the command line to analyze the movement of particles. It is not intuitive and difficult to analyze. In DVTOP, researchers can see the dynamic images and easily control the process. We can click the play button to start the analysis process. According to the analysis demand, DVTOP can speed up, speed down, and pause. Take PSO as an example. PSO is an algorithm inspired by the movement of bird flock. The movement of particles is guided by three forces: their own best known position P best, the best position among all the particles G best, and their inertia. We use a big bird to represent the G best, small bird represent particles, and the bird footprint represent tracks. Researchers can also adjust the brightness to see the particle tracks more clearly. And the left button tag shows the current best solution. The right button tag shows the current evaluation times. Researchers can use them to judge the quality of the algorithm. Now, researchers can see that all the birds gather together. In this situation, researchers can use the mouse to zoom in or zoom out the solution space to observe the movement of birds in detail. And we can click the auto to distribute the color, drag the generation bar, or enter a number, can observe the specific generation more conveniently. Besides, the particle tracks far from the current generation, the color will gradually turn white. We can observe that PSO searches the same place repeatedly, which causes lots of evaluation times to find the current best solution. Therefore, the Jaga algorithm is invented. DVTOP also has a comparison function that can compare the different algorithms, and we can take pictures or record the videos. Take PSO and JA-soft absolute function as an example. Compare which algorithm can find the optimal solution with fewest evaluation times. When there is only one algorithm, the displaying information takes the generation as a unit. For the principle of fairness, when comparing two or more algorithms, the displaying information takes the number of calculation times as a unit. We can see that JA converges quickly in the 646 evaluation and find the best solution 0. But PSO still slowly converges to the best solution. So we can note that JA is better than PSO in solving the absolute function. Besides, DVTOP provides the combinatorial optimization interface to demonstrate the different properties of problems. Taking the genetic algorithm solves 0-1 knapsack problem to demonstrate. The black means selected and white means unselected. Each row represents the best solution in the generation. As the generation increases, the previous generation moves up and the colors turns gray. The bottom row in red is the best solution found so far. The left number is the corresponding generations, and the right number is the fitness of that generation. GA's evaluation way is to select the best parent chromosomes, then do the crossover to produce the offspring chromosomes and try to find a better solution. For the convenience to demonstrate, there are 10 kinds of items, and the numbers of each item is 10. The item's cost-performance ratio in the 0-1 knapsack problem is high to low, from left to right. DVTOP can also show the detailed information to assist researchers in analyzing algorithms, such as the weight of the 0-1 knapsack problem. As the iteration increases, the black blocks are concentrated on the left side, which means GA select the higher cost-performance ratio items. Besides, some algorithms need to use the probabilistic model to determine whether bits are 0 or 1, such as randomized algorithm, estimation of distribution algorithm, quantum-inspired algorithm, and the stochastic algorithm, and so on. To click the dice button, the interface will change to the probabilistic model. In this model, DVTOP uses red to blue gradient color to represent the 0 to 1 probability. At beginning generations, we can see that the interface is all green. Every combination's probability is 0.5. The selected and unselected has the same chances. As the generation increases, researchers can see the color gradually changes to blue or red, which means the probability turning from 0.5 to 1 or 0. Blue ones have a higher selected probability, red ones have a lower selected probability. Using enlarged can observe every solution in the current generation. We can find that though the probabilistic converges to 1 or 0, each chromosome still can choose the solution different from the probabilistic preference. We can easily find that there are a few red lines in the blue area. The algorithms give some higher cost performance ratio items and takes the lower cost performance ratio items on the right side to make the capacity limit. This is the reason why the 0-1 knapsack problem is an MP problem and makes it so difficult and interesting. Besides, researchers can use the convergence graph to observe the fitness and compare the different algorithms. The x-axis is the number of generation, and the y-axis is the fitness. By observing the convergence graph of GA, we find that the fitness of GA jitters rising and still looking for the best solution. That is because GA chooses parent chromosome from the mating pool to cross over, and then produce the offspring chromosomes. Therefore, the best solution is not certain to be preserved. Therefore, QTS is invented, which uses the best solution found so far to guide. Observing the convergence graph of GA and QTS solve the 0-1 knapsack problem, researchers can see that QTS finds the best solution 620 at about 80 generation. This is far faster than GA. In a convergence graph, DVTOP also provides a function that can compare algorithms' best solution found so far in each generation. Besides, DVTOP also provides a map mode for users to observe deployment optimization problems. When there are crowded activities, such as New Year's Eve and campaign rallies or concerts, how many base station sites we need and where to provide the acceptable quality of the internet signal. In map mode, researchers need to meet every position's limit detection probability, or we call it threshold, with fewer sensors. In the map mode, the red to blue color means the high to low detection probability, and the black blocks are sensors. In this uniform map, the threshold is that for each position, the detection probability should be larger than 0.3. In the 5x5 solution space, it only needs one sensor to meet the threshold. And in the 10x10 solution space, it needs 4 sensors. In the 20x20 solution space, the area is 16 times the original map. It may need to use 16 sensors to meet the threshold. However, the sensing probability is 1 minus the probability of not being detected by all sensors, which means the probability that detected by at least one sensor. For example, when these positions sensing by over 2 sensors, their probabilities will increase and from green color to yellow. So, in this solution space, it only needs 12 sensors to meet the threshold. In a 50x50 solution space, the complexity is 2 to the 2 power of 2500. Now we need a meta-heuristic algorithm to help us find a better solution. This is a solution that QTS finds. In this problem, the number of sensors, GBAS, is 62. DVTOP is also a checker for the solution. If the solution meets the threshold, the word complete will appear, or the map completion rate will display. Through DVTOP, we find that some sensors can remove. First, we can directly remove one sensor at the bottom left corner. Next, at this area, we can remove 3 sensors and put 2 sensors. It still meets the threshold. Through the visualization, The best solutions that the algorithms find can be easily reduce the numbers. The analysis can be more intuitive. In some deployment optimization problems, sensors also need to meet the complete connectivity of the entire map within a limited distance. Such as the fire sensing problem, sensors need to monitor the temperature and humidity and send the survey data to the data center. Researchers can see the connection between each sensor. DVTOP is dedicated to explain how algorithms work. With the help of DVTOP, the algorithm's execution process demonstrates more intuitive and more easily understand. As the DVTOP can make researchers observe algorithms more clear, DVTOP can greatly assist the development of XAI techniques. Through DVTOP, teachers can explain optimization problems more visually interesting. Students can also understand optimization problems and meta-heuristic algorithms more thoroughly. And researchers can use DVTOP to obtain more information for analysis, improving the researching efficiency and even make the debugging easier. That's all for our introduction video. Thanks for watching.